Good day everyone. Today we're gonna tackle about Milankovitch parameters. The Milankovitch parameters, also known as Milankovitch cycles, were developed by Milutin Milankovitch, a Serbian mathematician, astronomer, and geophysicist. In the early 20th century, Milankovitch formulated a mathematical theory that described the cyclical variations in Earth's orbital characteristics under influence on climate. Milutin Milankovitch, born in 1879, was a Serbian mathematician and geophysicist who developed the theory in the 20th century. Initially, his work was not widely recognized and it took several decades for his ideas to gain acceptance. Milankovich's work was influenced by earlier observations of ice ages, particularly the discovery of Kerlik Ice Age patterns. In 1920, Milankovitch published his theory, which was based on mathematical calculations of Earth's orbital changes. His theory explained how small variations in Earth's orbit over thousands of years could significantly influence the planet's climate. Milankovitch was also able to correlate his orbital theory with the timing of past ice ages. In the Milankovitch cycles, there are three parameters which are called eccentricity, obliquity, also known as axial tilt, and precession. These three factors together describe the variations in Earth's orbits and tilt that influence the amount of solar radiation reaching different parts of the planet over long time scales. And now let's talk about eccentricity. Eccentricity refers to the shape of Earth's orbit around the Sun, which varies from nearly circular to more elliptical over a cycle of approximately 100,000 years. Impact of eccentricity. It influences the distance between Earth and the Sun. It also affects the intensity of seasons. This would mean that a circular orbit keeps Earth's distance from the Sun more consistent, leading to stable solar energy. An elliptical orbit increases the variation in Earth's distance from the Sun, intensifying seasonal differences. Example: 100,000 years ago, Earth's orbit was more elliptical, contributing to the last ice age. During elliptical phases, winters can be longer and summers shorter in specific regions, affecting glacial buildup. The implications of this is when Earth is farther from the Sun, cooler summers may prevent ice from melting, encouraging glacier formation. Conversely, warmer summers during elliptical phases may accelerate ice melting. And now let's talk about obliquity or axial tilt. Obliquity refers to the angle of Earth's axial tilt relative to its orbital plane, ranging between 22.1 degree and 24.5 degree over a 41,000 year cycle. Impact of obliquity. It determines the severity of seasons. It also affects the distribution of solar energy between the hemispheres. The axial tilt of Earth determines how much solar energy each hemisphere receives during summer and winter. The tilt oscillates between 22.1 degree and 24.5 degree over 41,000 years. Greater tilt closer to 24.5 degree increases temperature extremes between summer and winter, while the lesser tilt closer to 22.1 degree moderates seasonal differences, making summer cooler and winters milder. Examples: during periods of high axial tilt, regions like northern Canada experience intense summers, leading to greater ice melt. During low axial tilt, summers are cooler, allowing glaciers to grow. The implication of this is that this affects long-term shifts in the Earth's climate, especially during ice age cycles, when axial tilt can determine how much ice accumulates or melts. And now let's talk about precision. Precession refers to the wobble in Earth's axis of rotation, which completes a cycle approximately every 26,000 years. Impact of precession. It alters the timing of the seasons in relation to the Earth's position in its orbit. It modulates the intensity of seasonal differences. Precession refers to the wobble in Earth's axis of rotation. This changes the timing of seasons in relation to Earth's position in its orbit. Over a 26,000-year cycle, Earth's axis traces a circular path, altering when each hemisphere points toward or away from the Sun. This modifies the intensity and duration of seasons in a given hemisphere. For example, currently, the northern hemisphere summer occurs when Earth is farther from the Sun, making summer less intense. In 13,000 years, precession will reverse this, and summer will occur when Earth is closer to the Sun, intensifying northern hemisphere summers. The implications of this is that precession can amplify or reduce the effects of eccentricity and obliquity, creating periods of extreme or mild climate conditions. Combined effects. The combined effects of eccentricity, obliquity, and precession drive long-term climatic changes, such as glacial and interglacial periods. These cycles are collectively known as Milankovitch cycles. The interaction of eccentricity, obliquity, and precession creates complex climatic patterns over tens of thousands of years. These combined effects drive Earth's glacial and interglacial cycles. For examples, around 20,000 years ago, during the last glacial maximum, a combination of lower axial tilt, eccentricity, and precession created conditions for extensive ice sheet growth. Around 12,000 years ago, these parameters shifted, initiating a warmer interglacial period. The implications of this is that understanding these natural cycles helps scientists differentiate between natural and human-caused climate changes. Relevance to the 21st century. Milankovitch cycles explain long-term natural climate changes. Current climate change is dominated by human activities such as greenhouse gas emissions. Understanding these cycles distinguish natural variability from anthropogenic impacts. While Milankovitch cycles explain natural, long-term climate variability, they cannot account for the rapid climate changes observed today. Current warming trends are driven primarily by human activities like greenhouse gas emissions, deforestation, and industrializations. For example, natural Milankovitch cycles would predict a gradual cooling trend right now, but instead, global temperatures are rising due to anthropogenic CO2 or carbon dioxide emissions. Current atmospheric carbon dioxide levels over 420 parts per million are the highest in 800,000 years, far exceeding natural variability driven by the cycles. So, in conclusion, Milankovitch parameters are fundamental in understanding Earth's climate system. Their cumulative effects emphasize the importance of long-term changes. Milankovitch insights combined with modern tools continue to guide climate science. Milankovitch work laid the foundation for understanding Earth's climate system. Combining Milankovitch insights with advanced technology enables a deeper comprehension of climate systems and informs solutions for current and future challenges. For example, by understanding Milankovitch cycles, scientists can model how natural processes like ice sheet dynamics interact with human activities, helping to create better strategies for mitigating climate change. The key lesson from Milankovitch cycles is that while Earth's climate naturally fluctuates over millennia, human activities have disrupted this balance, leading to unprecedented changes.